to come to the AA now for quite some time, probably for almost a year and a half. And I'm really pleased that we have the exhibition of the bridge, which is going to be the subject of the talk tonight. I first met Marcel probably about six and a half years ago when he was teaching at Harvard. And I can't tell you the way in which that studio worked, his commitment, his passion as a teacher, and in a sense the results that I think he managed to produce in that studio was just fantastic. I think he's really a rare architect in terms of the way that he has managed to combine his passion for architecture and on those few occasions when he's decided to teach, to also carry that passion through to his teaching. The Murau Bridge that we are exhibiting upstairs is really the first of two projects that have been completed recently by the practice that Marcel runs in collaboration with his partner, Marcus Peter. This bridge is also, of course, done in collaboration with the important Swiss engineer Jacques Concept, who is also here in the audience, and we're very happy to have him here. Of course, also the practice has just finished, as you probably know, a single-family house, and is in the process of completing the timber school that has been published and which was started before, in fact, the bridge went on under construction. Right now, the practice is also involved with a number of other projects. There is the training center for an insurance company in Switzerland, and the competition-winning scheme for the new roof structures for the main railway station in Zurich. One of the things that I think we are going to, in a sense, hear about, and I think, in a sense, is somehow typical of the attitude of the practice, is that it's very much involved with kind of reworking the whole issue of materials. For example, in the timber school, I think there's a very different attitude towards the use of timber, and I think this is something that Marcel will talk about in relation to the bridge. The practice is really committed to the idea of pushing somehow the use of materials so that there is a kind of condition of destability or destabilization that is worked with a much more abstract, for example, use of wood rather than the usual semantic associations of materials that we all know so well. But at this point, I think we should all really welcome Marcel and hear the story of the bridge. Would you join me in welcoming Marcel Meili?
Good evening, and thank you very much for the invitation. I got this invitation from Mohsen Mustafawi, I think it was 9 months ago or something like that, and we were asked to present one single project, but if it is possible with all the plans about construction, about material and things like that, and I have been also supposed to explain how things in these projects are made. I could imagine that maybe one of the reasons why he was interested in the project in that way is also because there is obviously, or was obviously, certain tradition of making architecture, of craftsmanship, of construction in Swiss architecture now for decades or almost centuries. And at least up to now, I have to say that our working condition used to be on that field within our profession quite positive, but they change now, and maybe we can have the first pictures. And during the work for the exhibition, I had a very strange encounter. I think it is a kind of an encounter also with our future, because we were working on a renovation of a city housing project, and we were interested in some hinge for a window that opens from the to the outside, and we were therefore in touch with an American firm because they produce this kind of hinge, and we called them. We have American architects in our office, and to fax us this detail, and after 2 hours we had a fax of about 48 pages, and we had 2 days later, so we had this model in our office. We didn't order that, so I think it must cost like $200 for DHL to transfer it. And I was looking at that, and actually then it came to my mind that maybe it's really important to talk about the question of making architecture. Maybe it's also a story about the past, at least what happens in Switzerland. We are looking a little bit closer at that window. It's a kind of a metal wood window, the next picture. And you can see that even this demonstration model has this kind of, this kind of gap between the sash and the frame. The joint you have to look at, maybe it's it's unbelievable. This is a kind of, and it's not a transportation damage. It's a demonstration. And the next ones, and even if you look at the section, you can see how it is like. This is a sash of about 3 centimeters, which I don't know how it lasts. The sheet metal is 1 millimeter on the wood, and the connections are made like that. And when I saw that, I took an old pocket calculator, which didn't work at all, and cut it, and it's the same. It's not so much about the technique, but it's a kind of a question of expression. It's somehow the same thing that happens with that new technology, which now will invade, I think, Europe and Switzerland as well. Also look how these frames are connected or composed or things like that. It's unbelievable. And it's not so much that I think it is not precise enough, or it's not my soul of a watchmaker that has some problems with that, but it's more. It's more a problem of expression, or what things really mean when they are produced. I think every material, every construction does talk. Material for us as architects is maybe somehow similar what the color is for a painter, and it's not so much the technique that has to be in a certain way as it has had in the 19th century in the academies or things like that, but it expresses something, and also this window talks about something. It talks about speed, it talks about wear, it talks about a kind of package mentality, it talks about a complete uninterested attitude towards craftsmanship and things like that. And somehow it's more a copy of a window than a window itself. It looks a little bit like the American were talking about the Japanese cars of the 60s, which were, in their eyes, were copies of the American and European cars. And it's not so much, my problems are not so much about that if things are cheap, because we'll see the project I'm going to talk tonight is also all other than expensive, but it is a problem of mentality. And so I want to talk tonight about our interest into material, into construction, into static. And as you know, there is also maybe a danger to talk mostly about this aspect, because especially in Switzerland there is a certain mania in precision and things like that, and things that are well done are also good things in the head of the people, which I don't share at all. It's not so much that we are interested in the material itself, in some single aspects, but as let's say in two specific aspects. Construction for us is part of the syntax of the architecture. It's not so much about reduction of things, so that we try by material and by construction reduce or make things more abstract, but it's more about construction of things that last, that somehow are able to express something. That's one aspect, and the other aspect is, let's say, the conceptual or immaterial or intellectual dimension of construction of the material. The materialization of our projects are not the materialization of an idea, but they are part of the idea itself, I hope at least. When we, for example, tonight talk about wood, so for us, wood is also something that has a certain tradition, it expresses something, it has certain values that are connected to it, or some semantic history, a certain expressivity, a sensual property, which can be coziness or cheapness or transiency, or the fact that wood is a material that's always joined. So that means when we deal with materials, that doesn't mean necessarily that we work with that traditions in a positive or affirmative way, but also maybe in a critical or manipulating way, as we can see. But all in all, still, if we deal with material like wood or concrete or glass or everything, is it not only the technical or physical aspect that interests us, but also the aspect of the material that happens in the mind, you know, that it moves something in your brain or in your soul, and that's what interests us. The next. So it's actually the reason why we choose the bridge to demonstrate something tonight. First of all, we choose the bridge because it is actually not a building. It's a kind of an engineer's piece. It is quite cheap. I mean, this bridge cost about, I don't know, 400,000 pounds or something like that. It is very simple. Everything is open. One has the idea that one can see every part of the construction, and it seems to be very simply assembled. Everything is visible, but everything is secretly held together by statics, by structure, and by some technical processes. And the second reason why we choose the bridge is because I think it is, and I didn't know when I was invited, I think it is a problem to have architects build a bridge. I heard that in London at the moment there is has been a big competition about living bridge or something like that, and I have only seen some small pictures of 2 or 3 projects, and I thought it might be interesting to have a kind of an antithesis to that, because our main effort to this bridge was not to separate the architectonic from the static interest or idea, but to bring them together up to the point where the structural aspect and the architectonic or sculptural aspect is inseparable. So we try to work with the static or the engineer aspect, which actually is not our aspect, and therefore we had to have a very gifted engineer to help us and to do it together with us. We try to work with that static or engineer aspect as we do with construction, with material, with volume or space or light or everything. So I'm going to do tonight something that I usually do never do, and maybe one shouldn't. I'm going to explain one single project, by the way, to take it apart and to explain all the steps that are behind that process and all the aspects that produce the form of this bridge. I think this didactic game may be allowed because it is not an architect's work but also an engineer's work, and engineering is for us still something let's say, kind of a dark hole, which is hard to understand also for us who are interested in these aspects. So let's start, the next picture please. Let's start with the bridge itself. The beginning was a competition that invited 7 teams of architects that could choose their engineers. It was in, as you know, may know, in Austria. It was an international competition, and these 7 teams were supposed to submit a proposal for a covered wooden bridge, which should be part of a big wood exhibition in that town called Murau, and which should demonstrate new technologies in wood, and which was supposed, the bridge, to last after the exhibition. That shouldn't be destroyed after that. So when we started, we wondered how to deal with that problem, that this bridge should be out of wood, because there are only 2 or 3 ways traditionally wooden bridge are constructed. One is this kind. This is a bridge in Java in the 17th centuries. It was the pictures of the 19th century. It's one of my favorites. Actually, it's fantastic. It's of bamboo or something like that, and it's a kind of a hanging bridge, which has also kind of truss or something like that. And one really can't exactly understand how it works. But you can see one of the basic aspects of wood, that it is usually a linear, a bar-like element, which can be composed, for example, to some hanging thing or to an arch which is under pressure. Also, this is a Japanese bridge, also of the 18th century, in which you can see this kind of composition of these linear elements and the additive, the composed aspect of the construction. That's the first type. The next one, please. The other type of bridge, which is very common and which I like a lot, is the truss bridge. And you have a kind of a 3-dimensional truss which is covered by wood boards, and which has a big tradition in the Alps, in Switzerland, in Austria, in Germany, in France as well. And when we started with that, we had the aim, or we had the idea to completely change these systems. And the next one, and we came up at the end with that scheme. Actually, the scheme is very simple. You have 2 chords, an upper chord and a lower chord, and 2 types of kind of shear walls, here one and here one, and thank you, and a second bridge which connects, as we can see, by a stair, another point and on the riverside. And on the right-hand side, you have the type of section with these 2 chords, with a type of bar on it to support the roof, and a bar on the bottom to support the floor. So this is actually the system. Now, to understand how that worked, I have to explain how it came that we developed this type of, I think it's a new statical or structural system, not only in wood but also maybe in concrete or something like that. The next one. First of all, there were 2 reasons. The first idea we had was, these are the end sections with these hollow shear walls on the end here. The first idea we had was, the next one, was that we took a law of building wooden bridges and somehow perverted it. And this law says that traditionally, for centuries now, you had a bridge with a kind of, for example, a truss or a structure which is made entirely by wood, and which, in order to be protected from the rain, has to be covered by a secondary element like the roof or the wall, which can be the railing or I don't know what. And we thought it might be interesting to develop a wooden structure which shows the quality of the structure itself. So this was a a Swiss bridge of the 18th century, which doesn't stand anymore, unfortunately, which is a fantastic structure, in my opinion. But it was completely covered, of course, in the same type as this one here. And therefore, we tried to develop a structure which protects itself by the roof. The next one. So the basic idea, this was the traditional type. The basic idea was to work with only one truss in the middle and to have a roof and the floor on top, like in with a double T-beam or something like that, which protects the open truss from the rain. Then we had the problem was that that would make two separated spaces on the roof and separated two ways on the bridge. And we tried to find some system which would allow to connect these two spaces. The next one. And therefore our engineer came up with that Brunel bridge of a truss which was that big, that extremely with that large fields that it starts to lose its character of a grid and seems to be composed by single elements. So we try to introduce a truss with only three enormous fields of about 15 meters or something like that. But there also in this scheme we had this kind of diagonal which in the middle which would somehow separate the two spaces, even in the case when you could, for example, pass it, as in this. I mean, this is a very Hebride thing which we liked a lot. But we then, the next one, continued in trying to somehow to avoid this separation of the spaces, and the engineer suggested then to make this the upper and the lower chord that strong that it might keep in the middle without any diagonal, and on the other hand he would make the other fields on the side, these two fields, these two diagonals, very, very strong. So we had a kind of a window in the middle which connected the two paths of on the bridge, and from there it wasn't too far to the next step. The next oh well, sorry, I have to go back. That comes later. Maybe I have to, first of all, I have to explain how that statically works. I didn't know that before as well. So it was developed during the competition. So the next step then was that we covered this, the end fields and left away this kind of diagonals and made this the last fields kind of shear walls. And this system works as follows. The next one. The traditional truss, as you may know from your education as static students, as architects as well, under pressure does some load, some stress on the diagonals, which can be in this direction or under pressure as well in the other direction. The system we choose is a kind of a perversion of the so-called Vierondel system. The next one. The Vierondel system was developed in the steel structure for bridge at the beginning of the centuries and avoided this kind of diagonals by, as you know, in the truss you have here this kind of joints which aren't stiff at all, and Vierondel, a Belgian engineer, tried to avoid these diagonals by making these joints completely stiff, so that every vertical post somehow can take this a certain amount of shear stress without connecting one joint diagonally to the other one. And what we made now is the next one is actually a kind of, this is one of the first Vierondel systems. I think it was a railway bridge or something like that, and this is a typical stiff Vierondel system connection in the edge. The next one. And what we then made out of it was a kind of a Vierondel system with extremely huge posts, which are this kind of walls, and with enormous strong cord, a very heavy cord in the middle. That means that you, of course, have in these edges enormous stress, because the bridge has about the size of 50 meters or something like that, which isn't too small. It's also not too big, but it isn't too small for a wooden bridge. And these shear walls here now work like the posts in the Virondale Bridge. So you move all the stress from the middle through this point into the walls, and this deformation, I mean, it never will deform like that, of course, but it shows you how it really works under stress. The next one. So the other reason was, now we had a kind of a system which was perfect in our opinion for our first target, that we had the structure in the middle of the bridge, and it was protected by the upper cord and by the lower cord from rain, so we hadn't to cover it anymore. And the other reason why we came up with this scheme was the site. This, the site for this bridge was really actually a fantastic situation. We will see that afterwards. It allowed us somehow to concentrate all the stress on the riverside and to open the middle on the window. So we didn't interrupt the river landscape, and you will see afterwards exactly why. So we have enormous strong elements next to the riverside, and in the middle it's completely open. The next one. So the reason for that was the site in Murau. This is an old medieval town, and the bridge is somewhere here around. This is the site plan. This is the station here. And the main reason was that we thought, as I told before, the bridge had to be covered, and to have a 3-meter high bar over the river would disconnect completely this fantastic landscape here. So we wanted to introduce this kind of movement which allowed the space to flow through the bridge and to concentrate all the material there where, and this is fantastic on one side, I mean, this is very seldom, rare, that you can introduce a bridge in the middle of a town on one side and in a kind of a wood on the other side. So we concentrated all the material there where the plants, the trees and things like that, and the houses were. The next one, you can see that easily on the slides. So we had a completely, let's say, archaic rectangular parallel element which was introduced into this landscape, first of all, by a kind of a static paradox. That means that there where the biggest stress is in the middle, there is no single post, and only a little material, and all the stresses go to the riverside. That's one thing. And on the other thing, we had a kind of a form which made that piece, the bridge, like a piece of wood which was jammed into this landscape. You know, we always had the idea that this bridge should be like a piece of wood that came with the water and somehow jammed into that narrow. That's the narrowest part of that river in this area. The next one. The next one. After that, the finish, the bridge was finished, we were often attacked by engineers, because, especially by Austrian engineers, professors and things like that, because they said this bridge maybe it may work. Well, actually, it was very funny, because at the opening there have been, or after the opening, there have been classes of students, of engineering students, coming to look at it, and they have been standing there, and they really wondered how it worked. They didn't understand that, and so your concert always had to stand there, like in a, give answer and to explain them that it wasn't a trick at all, and it was a completely logical system, and it wasn't really to understand visibly for educated engineers. And after that, we often were attacked by engineers because they said, well, this bridge, maybe it will work, or it won't be destroyed by load, or I don't know what, but it's somehow against the law of readability. So this old modern thesis that an engineer's work has to be understood, visibly understood, how it works. And obviously that's not so easy to understand that, and they got quite aggressive. It was unbelievable. And therefore, next pictures please. One can really say that maybe focus it, yes, that it is somehow the engineer, which maybe was the most important person for that project, somehow disappeared with its work. The form the bridge has doesn't somehow demonstrate how stresses flow and how things are supported. It's a more archaic form, which has very basic elements, and it was always the engineers and our target somehow to produce a bridge which wouldn't play with that kind of rule or law that engineers' work has to work with engineers' readability. And so therefore it seems, I didn't know that in 2 days you will have the next one, you can hear the contrary, because Calatrava will be here, and I heard, and I didn't know that, so the slides have been in before, and so we did exactly the contrary. And Calatrava's target is somehow to work with the stress or the load and things like that as some visible quality of the form. And therefore, he also somehow is perverting this old law of honest constructions and things like that, because as you may know or not, all these things, also of Calatrava and all the other bridges, you seem to understand in reality work completely different. So when you really think that you understand how, for example, this roof really works, you know, with holding back some load and pressing down and here, things like that. This is completely manneristic, but it's not a critical look on it. It's just a description, because it demonstrates something that in reality works completely different. And it's maybe it's not so different, but it is much more complicated. Even this bridge, which seems to be easily to understand, in reality works as every bridge does, in a very, very complicated way. And I think it's a quality of the computer age that today we have the means that we really can somehow reproduce what happens in such a part, or also in our bridge, or what really happens in such a situation here. And I think that somehow destroys this idea of having a direct connection between how things are formed and how they really work in a structural way. And we can see that it's not only today like that, the next one, but it was always like that. Even the first bridges that have been calculated in the late 18th century, for example, here this example by Perronnet, the French, one of the famous early engineers of bridges, French engineer Perronnet, which tried to avoid the Roman arch, which brings the load on every post or on every column, and in an additive way. So here he tried it formally. He tried to make the arch more slim, more narrow, and then he somehow developed a system to calculate that in fact the stress is brought from one arch to the other up to the riverside, and that's something that allowed him to make the columns pretty much more narrow than they have been before. They were extremely wide in the Roman bridge, and they got slim and narrow in the late Pyrenees bridges. But you, as a visitor or as an architect also looking at that, you can't really understand how it works and why it works like that. And it was always, I mean, the history of engineering is a history of hybrid system, and all the other things are kind of propaganda. The next one. So this is another of our favorite bridges. Also Brunel, a British engineer, English engineer of the 19th century, and this piece of architecture, I mean, it's fantastic. It's completely hybrid. It was some things are calculated, some not. You have kind of an arch under pressure. A part is hanging. Then the horizontal piece for the train somehow brings or makes that the load doesn't go to one single cable or whatever it is, but is spread to the different cables and things like that. This is, I think, what engineering is about. It's a kind of, you can calculate a lot, and in reality the things are very hybrid and very pretty much more complicated than we always think. That's even the case for Robert Meyer, one of next please, the most interesting Swiss engineer. I mean, this is one of the bridges of the high time of modern dogmas about how engineers' bridges should be made. You know, they should be clear and understandable and things like that. But if one calculates today what really happens in such a bridge, you never would expect what really works here. For example, in this part here or so. So I think this is a fantastic piece of architecture here, but it has nothing to do with kind of honesty or something like that. The next one. And I think the result today is that even in the time of Meyer, especially of course in Brunel's time, it wasn't exactly to calculate how a bridge really works. But today, with the new methods of calculating bridges, with the computers, we really know more or less what happens, and that allows us now to play with stress, with force, let's say like with a collar or something like that. And it's what we try to do. So we are able, or not we, but our engineer is able to bring load from here to the riverside, or he could even make the contrary or things like that. So that gives an enormous freedom if one really works with the engineer and makes a kind of a research about it. So you can start the stress starts then to be like material or like a collar or something like that. And that was what interested us, so that we could, by these methods, we could work. We hadn't to follow some laws or dogmas or things like that, but we could work with that in a very free way. The other thing I started to mention, the next one, was about the problem of the wood. I told you that we wanted to make a construction which is like a monocoque body or something like that. So things that support the load also are the parts that make the form and that are visible and that organize the space and the sculptural qualities of the bridge. And since I told you that we wanted to work with or to make a kind of response to the powers to the load by very heavy or straight elements, we were interested in using the wood in a non-additive way. Usually, as you know, wood is that material that is that's living by joints, by a hierarchy of small, medium, big, and very big elements, and we try to use the wood as a completely homogeneous material. And the next one. As you can see, this this bridge is made out of a system which I'm going to explain now, which is not like joined anymore by beams or bars or things like that, but most of the things are glued together, and it makes a complete homogeneous surface. And the surface actually is not only a surface, but it is what you are seeing here is what supports the bridge. This is the upper chord, for example. This is the hollow shear wall here or here. And all the things are actually the material that supports the thing. How is that made? The next one. I think this is I don't know whether that's known in Great Britain as a system. I didn't know it before either, even if it started, the firm started to produce with that system a couple of years ago. I don't know the English term for that. We call it Brettschichtholz, which is a system that is based on bars of about 30 by 30 millimeters and a certain length which you can have from I don't know what, and then they are glued together to boards, and in a way that they are that they can be joined almost without any end. So you can have a board of about 12 meters, or maybe that by the end of the transportation system, I don't know what. And if you have such like boards, you again can add them to a kind of a beam or so. They are all glued together. It's a kind of a three-dimensional plywood technique. One could say it's not plates or sheets or things like that, but it's this kind of bars. And if you have these beams together, you again by a specific technique of nailing, you can glue together these beams to an enormous mass, and that makes, I think this is very interesting, even theoretically, because it makes, theoretically you have a homogeneous but completely infinite material out of wood. Of course it's directed by the fiber, but it can grow in every direction. And since it is very cheap wood, because the basic element is very small, the cost of the material doesn't play any important role. So it can grow in this direction, or in this direction. And this is the base behind that design. The next one, we can see that under construction. So how they are glued together, they can be prepared in almost every form. So actually the wood here starts to be a kind of a mass. You know, it's a homogeneous, directed mass, which you somehow starts to have some similar properties to, for example, to concrete. And it was also an objection to that bridge that it's not so different to a concrete bridge. And then we said yes, that was exactly what we were interested in, because it was cheap, and it has a kind of it starts to have a kind of a body expression which wood usually doesn't have. So it has a certain weight and a certain power by some like sculptural expression, by this density of the material. And in difference to concrete is a kind of self-reinforced, because the fibers, of course, other than concrete, are able not only to accept pressure, but tension as well. So you have a kind of a self-reinforced material, and this was actually the basis of that design. Out of that we made everything. The next one, the whole bridge except the railings is made out of that. And especially not only the upper and the lower chord, but also these walls. And these walls had for us an important meaning in the whole design, because of course they are hollow, but they have walls of about 12 or 15 centimeters, and this is about a size of 90 centimeters. That's extremely heavy. And these walls are introduced in the design in order not only to support the bridge, but also to connect the different paths that had to be connected by that bridge. So we were supposed to connect 3 different levels and 4 different paths within the bridge. So the bridge actually is a kind of a crossing or some kind of a carrefour or something like that. So you have the main station here, and with the stair bridge going down, and then you have for bicycles and for other vehicles a kind of a path which without stairs here. Then you have this kind of promenade boulevard here, which is on the lowest level, and the connecting point to the village is on the upper level. The next one. So here you can, and this was one of the interesting conditions we had, that we could make a bridge which is completely uncommon, which connects 3 different levels. This one here, they are almost the same, and about 8 meters or more higher the station. And now these walls then had the meaning to somehow to receive all these different paths and to guide them to the middle, to the central space or square or whatever it is. The next one, we can look at these other pictures. So you have this spatial, or let's say, path meaning of the walls that somehow receive all these different paths and guide them to the middle. And here you have this kind of crossing of the 2. This is the way for the vehicles and the bicycles, and this is for the pedestrians. Next one. So we also always had then the idea that this bridge by these walls should be, the whole bridge should be one piece of wood, which is like split. You know, this is so we wanted to make it completely homogeneous, and then somehow to split it, that it has kind of arms that then touch the landscape. The next. We call that the death wall, because we waited the moment when the young bikers come, and well, it's quite okay, we leave it. I mean, it's maybe an insurance case. The next one. The next one. So looking on the roof, you see something. The last point that I want to explain, it's why these walls are shifted out of the axis. You can see that these walls are not in the axis itself, but they are shifted out of the axis. The next one, and this was actually one of the big arguments we had with the engineer, because it was made him a lot of problems in terms of torsion. And I think Jacques spent many weekends to follow our argument that we never would accept a wall that would be exactly sited in the axis, because we had a feeling that this kind of blade of a knife would separate again the spaces, and we had some other ideas. So we suggested to organize them on the side of the upper and the lower chord, and you can easily see why. The next one. The reason actually was that we always saw this bridge like a building on the water. It was not so much about only a connection of points, but we saw it somehow in a tradition of that Palladian bridges, which now are also, I think, the images that are in the mind of the people that organized that competition here in London. So we saw it actually in that tradition, but not in a way separated between the bridge and the building as it always was. So we wanted to organize the space on the riverside, on the river, in a way that it's organized completely by the static elements. The next one. And the other tradition, of course, which was interesting for the building on the water, was this kind of truss bridge, the traditional truss bridge. But also this space is a kind of a tube, a connection between points, and we wanted to organize it more in a way that the space somehow comes to a certain quietness on the water. The next. Of course, the system we were developing somehow is related, or seems to be related, to a certain style tradition where one organizes the space only by walls. But actually we had quite a different idea. You can see that in the difference between a medium and an early Mies van der Rohe building. The next one. So this famous Barcelona pavilion somehow gave us some ideas how that space should be organized. So by walls and the roofs and the floors that somehow are not like in the Dutch, the style buildings, the end of the building, so the wrapping of the building, but somehow in the middle of the building and organizing, activating a space that this is completely open. But in contrary to the Barcelona pavilion, we were more interested into this very early scheme of Mies van der Rohe, where the elements had a certain, let's say, materiality, a certain thickness, and a certain sculptural presence. And the next one, and we had the feeling that if we would organize it, this is about, I think, 80 or 90, 80 centimeters or something like that. This very heavy element couldn't be in one axis, because then it wouldn't work as we saw it as kind of directed or directed columns. So they should have a certain autonomy, and not a kind of a knife, a blade of a knife that cuts the space. So we separated the out of the axis in order to make them somehow independent, working as a sculptural, as a material element for its own. The next. So this is the space on the bridge itself, which actually was the main subject of the whole design. The next. The next. And here on this, that's difficult to explain because it's very hard to see that in the pictures. But in reality, you can see that it's really very important that these, which is now visible for the space in the middle, that these walls are shifted. But there is, of course, another reason how that scheme was developed because or concerning that shifting out of the axis. The next one. This is the space in the middle with this kind of ribbon window without any post. That's the point where the heaviest loads are on the bridge. The next one. So one day I came and I was quite astonished about that because we had a lot of problems with that with the community there at the beginning, and they were extremely against it. But at the end, they accepted it really as a building, and they make now parties on it. And when I was so shocked when I arrived on this day that I forgot to make that picture. But there was a kind of a popular Volksmusik chapel on the bridge, and they roasted. They had on the floor there was it was all wet of beer, and they roasted sausages, and this was incredible. And okay. That was the space, but actually that was the idea we had. It was a kind of not exactly the party, but that it was conceived as a space on the water. The next, this very slim section I mentioned before made the engineer a lot of problems, because the next one. He had enormous problems in avoid this kind of torsion in the shifting like that, because the section was that narrow, and so that's the reason why this hat section was made, so that the upper and the lower chord somehow are a little bit stiff to avoid this kind of torsion. The next one. And this one was, it's maybe more interesting for the architects or for conceptual reasons. For us, it was quite interesting or important that the section in the longitudinal and the cross section has somehow the same type. So this kind of window or the eye, as we call it, in the middle, the open space in the middle is in both direction organized, and actually, it works in both directions. Of course, in the longitudinal direction less, but it works as this kind of Virandel-Träger I mentioned before. So the stiffness of the two walls helps each other against this torsion. But the next. But the main problem, this is kind of the explosion drawing that shows the last point I'm going to explain. It's about the way it is constructed or built, actually. So the whole thing is prefabricated. It was made in a firm which was 800 kilometers from, or 600 kilometers from the site, next to the Swiss border, and it's actually built up like a set, like a toy or so. When I was a kid, I had this kind of Revell airplanes, and they had always this kind of drawing. So we were interested in showing how things are put together. Everything is prefabricated, and that was the next one. Not so easy, and this is the last point I want to, even if it is very technical, maybe boring, but these are things you have then to solve if you want to develop or investigate such like systems. As I mentioned before, this Vierondel system produces an enormous amount of stress in this kind of edges. And when we insisted in organizing the shear walls on the side of the upper and the lower chords, then of course the engineer tried to use the surface between these two elements to connect them and to organize the joint between the two prefabricated elements. And he invented this system of the ductile shear connection, which I'm going to explain now. The next one. The problem actually is that you have, of course, in wood a lot of tolerance problems. So if you would take screws to connect the two parts, the holes which you, of course, have to make in the workshop, they never meet each other precisely. So if you have on this edge where you have all these shear stresses, a number like dozens of screws, they may be organized the holes like that, so they don't meet each other. So if the stress comes and the two parts starts to move, maybe the first element will break before the other one even has some load. So this is a really, it seems simple, but it's a real problem, and therefore Jacques developed this kind of ductile connection, the next one, which is actually, I think it's a very interesting system. He took some tubes, just regular steel tubes, which then he introduced in this kind of nuts, and of course they didn't meet each other also precisely. But this system somehow is plastic or elastic, and the trick behind it is that, for example, this one can be deformed without breaking before that starts then to take load as well. And we tested that in a laboratory, the next one, and we could prove that even a completely deformed tube, that is has a deformation of about 3 centimeters, still is able to take the stress that it has to. So we were able, the next one, to make all the nuts in the workshop. These are the tubes then introduced. This is one of these hollow shear walls in the factory. So we could produce everything in the Vorarlberg, the next one, and made this process. So the whole, actually the bridge consists out of 6 parts, main parts, which were transported throughout Austria by these trucks. It was quite impressive. And then the next one, they were built up within 2 days. We can look at this. It was kind of a theater spectacle. Next one. So they were only pressed together by these tubes, and then some screws, but which do not take shear stress, were hold together all these 2 parts, but they only press the wood to the tubes. The next. And at the end, the next one, at the end there was a kind of a actually it's not a pre-stressed system, but the lower cord was connected by a post tension. So it's a huge cable which it's a kind of maybe the first wood that is pre-stressed or post-stressed with a quite a load. It was quite a heavy force that was brought into that lower beam in order to stabilize the whole system and to connect to connect the middle joints. Next. At the end, the middle post was taken away after a couple of days, and then the rest, the roof and the metal sheet and things like that, came. The next one. So actually, at the end of this explanation, of course I had to explain a lot of technical things because, as I mentioned before, I think it's without an interest even in that kind of practical, material, constructive, even engineering things, it wouldn't be possible to organize the scheme of a bridge in the way it was. But of course, at the end of our interest never was technique. It was even not construction, even not by the engineer, but it was the form and the space and the sculptural quality of the wood that interested us, and we used everything somehow to reach this target, this aim, to find this form which is like a non-engineering form. And I think the main lecture the main thing I learned by this, or we learned by this scheme, by the work on it, was that it really is possible to work with power in the same way as one does with material or with color or with things like that. The forces in this bridge are somehow like an invisible color, and the main idea behind it was to organize a kind of a modern space that gets its sensitive qualities by the fact that you really sense the forces or the stresses that go through the bridge. So these forces are, I think, an important invisible part of the part of you can sense to organize such a form and such a space. Maybe that in a couple of years we aren't able anymore to make a thing like that, because it looks like that in Switzerland and in Austria as well, they start somehow to avoid, by the reorganization of the professional field, to avoid such researches that connect the design interests even to the manufacturing, to the construction and to the material. It may be that this bridge is more like an expression of the past of our profession than of the future, because it could be that we aren't able anymore to work in that way. Thank you very much.
I'm sure there'll be some questions. I would like to start with one, which is really related to the issue of mass that you were discussing. I know that the presentation has been very specific on this one project, but if I may, I'd like to maybe get your reaction to a slightly kind of more general or wider territory. I think that the bridge is not really the only building. One could begin to think maybe of a number of other projects that are happening where we could say that there is a similar attitude towards the idea of form or towards the idea of mass, in where there seems to be a kind of resistance to this more accepted notion of structure and skin, the idea of cladding and so on.
Right.
And I wonder whether you might expand on that theme. Do you feel that, for example, the construction of the bridge itself is somehow a polemic, in a way, in reaction or in resistance to the idea of the lightness of structure or the lightness of skin, going for something which is really much more the mass, the solidity of the project, despite the fact that there would be a lot of lightness that comes from that solidity.
Yeah.
But nevertheless, do you see this as a sort of counter-polemic to lightness?
Well, I don't know. I mean, maybe the question whether it is a polemic is more a problem of people that conceive it as a polemic. You know, we didn't want to make a polemic, but we did want to make a statement. Yes, that's true. That I think somehow also in other projects, and I think we are not the only architects in Switzerland that somehow work in this, let's say, similar way. That specifically we are not so much interested in this kind of question of dematerialization, this kind of modern tradition of somehow ephemeric producing space and sculptural quality by ephemeric construction. So, I mean, maybe it's not so much against that, but it's more about that we think that maybe it's a reaction on the modern tradition, that we think that modernity, or a modern quality of space has nothing necessarily to do with the fact that it is immaterial. So we are looking for the material and we are looking for the stress, and but not in a traditional way, maybe. So, but, I think there is a connection between this kind of modernity on one hand and the expression of the material as a, let's say, as a thing that stands for its own and for the future as well.
Any other questions? There's Peter back there. Do you have the microphone? Peter, could you wait until you get the microphone and then I'll...
Thank you. Certain elements of the bridge are very massive, but there are several finishes used, several timber finishes, from plywood on the ceiling, boards made up of strips, solid sections on top of the upstands, and these finishes give the appearance of the bridge rather a light quality, and that was very clear from your slides. Could you say a little bit about those finishes and the system that lay behind their use?
Well, maybe, I don't know, there is not one, as far as I know, I think Jacques has to correct me, but there is not one single plywood panel. Even the panels that somehow protect the roof constructions, they are made of the same thing. They have a certain... That's difficult to show that in the picture, but I think the whole construction has a certain massivity, and it comes, or it's, so for me at least, it's rooted in this technique of gluing together this kind of wooden bars. But I never would. We discussed that, and then we avoided that because we thought that everything that every material that was used for that bridge should be somehow of the same heaviness or material presence. You know. Is that what you wanted to know?
Yeah, to give an example, the ceiling bridge.
Yeah.
There's whatever the detailed construction, the grain of the timber runs in two directions, so that.
Yeah, that's true.
So that the light acts on the two surfaces completely differently.
Yeah, I mean, we have another problem there. That's correct, and maybe that's even a mistake. But we had the idea that I mean, these panels, which has I don't know, this strength or so, they do not support anything, and we wanted to show that. But by there at the moment there is an enormous difference in the brightness of the colors. So the cord is very yellow and the other one is I think darker or so. But it's exactly the same material, and it comes only because it was the cords have been laying in the sun before they have been introduced into the structure. And now since that it's completely protected from light, it doesn't change. So it will take us years to that they get the same kind of gray, dark touch. But I think there is really a problem. It's I don't like this. I mean, these pictures have been made a couple of weeks after the opening a year ago, and it changed a little bit, but not much up to now. And I think this is so. We also discussed that fact, and we thought that if we would have, I mean, we had very little money and we had very little time to develop the whole scheme. And today, after the bridge was finished, we would try maybe to organize the money that there has to be no difference. I mean, that we could make the upper chord just the same, the whole width of the bridge, so that there is only one piece of wood. But there was no money at that time, and maybe we didn't insist enough to have it. I think it's a problem, yes.
I'd be interested in the role of the post-tensioning in the bridge, and exactly how it's accommodated within the chords which are built up in the factory.
Yeah, I could explain it, but maybe if we have the engineer here, maybe he can answer.
The reason I'm interested is because I saw the publication and I admired the bridge very much. On the other hand, that was the most puzzling aspect of it, was the ability for the lower chord to carry the weight of the whole thing. And with the exhibition here, I see the post-tensioning of that lower chord. And I was curious as to whether it was part of the assembly of the two parts, or whether it is the steel tenons, how they are accommodated within.
It's both. But maybe did you get the question? Maybe you come here so that.
I made it from here.
Okay.
First, the main reason for this post-tensioning tendon is that it was not possible to fabricate the lower chord in one piece for transporting and for putting in on the scaffold. These were very huge cranes to put these pieces together. And so we had to do a joint, more or less in the middle of the bridge. And at first we studied together with the contractor to make this joint of steel plates, big bolts, Gelenkbolzen with a lot of nails, things like that. And it never was satisfying, because it always was a weakening of the section at the point where the bending moments and the torsional moments are huge. And so at last we came up to the idea to push together the two pieces in a very simple way, and it resulted in a more cheaper solution. But in fact, it's only this joint that had to be pressed by the pre-stressing cable. The dimensioning is exactly the same if you have pre-stressing or not, because the wood is able to take forces. Well, it resulted as the simplest possible solution, which does not weaken the joint. Yes, exactly. And it was funny, when we did it, I recovered in a village nearby, in Villach. They did it before, about 20 years. But there they had two girders, and they carved in a cable in a curved way.
And so by the curving the cable, you can add external forces to the wood, but it's much more complicated to fabricate it. And so the cable was on site, pulled through the whole length of the bridge and fixed on these steel plates. And that's all.
Thank you very much. One thing that was one thing that's always striking about lectures that involve description of engineering principles is that an audience can be lulled into the suspicion that because it's engineering it equals truth. And I think one of the most extraordinary things about your lecture tonight is that you put as obstacles in the way of that idea the cultural content of your project, the relation of Mies, for example, and its effect on the project is something I found very extraordinary. And also the presence of Calatrava and this, as you called it, a kind of an illusion of structural truthfulness that comes from his work. Now, Calatrava, of course, is the superstar, and in a way, there is a kind of image to that work, an image of truthfulness, perhaps, which is problematic and doesn't acknowledge its cultural content. You, in making comments about Calatrava, described it as mannerism. I was wondering if you wanted to expand on that comment.
No, I think I said. I mean, as I mentioned, I didn't know that he will come, and you can see it. And it's I introduced that to a certain extent to show that in terms of form we do exactly the contrary. So that, I mean, we are not looking for this kind of like the form that somehow demonstrates a certain illusion of flowing stress and things like that. But where I think, I mean, I know a little bit the work of Calatrava, and where we have some similar things is, I think both our methods are not modern anymore in the sense that we follow even Calatrava. Maybe you ask him. He never, I don't think that he would ever, or even in earlier days, he never did insist on the fact that what he shows is what it works like. So he is completely aware, and maybe that's what the example connects, that forces or engineering dogmas are things that you really can work with it. And maybe he was somehow the first that, since he was an engineer and an architect as well, that knew, I mean, that knew that the gap between the architect and the engineers today is a kind of irrelevant. You know, this is, I mean, I learned a lot by, of course I'm interested somehow in statics or things like that. But if you have an engineer like him who is interested in architecture and you are a little bit interested in engineering as well, you can move the world, actually. So there is a lot of, that's an important thing, in my opinion, that one somehow loses this kind of respect of that so-called science of engineers. Engineering is interesting when it isn't a science anymore, but has to, or only a science anymore. And then, I mean, all this method, all these computers, the finite elemente method and all these things make it, I mean, if you dig a little bit into the things, you can see that there are so many things to move and to work with, and one should lose every respect of that. Not of the persons that do that, but there is not more secret behind the bridge than behind a house or something in terms of architecture. And that's not kind of disrespect, but it's the contrary. So that's interesting in engineering, exactly that this material, the knowledge is accessible even for us.
May I continue this a little bit further and ask a question which I think in a way relates to Moisen's question and comment at the beginning, and in a sense is very dumb, but preoccupies me very much, and in a way it's why I like this project so much, and it's a kind of question about where one derives meaning from in a project like this, whether this project is architectural engineering. Now, I found it interesting to hear you say at the beginning that to talk about Brunel's projects and talk about hybrid solutions. And in a way, and the other thing that I started thinking about later in your talk was issues that Zemper raises and ideas about style and tectonic arts. And in a way, what interests me is the idea that engineering can be a sort of contributor, but is it a driver towards an aim one has for a solution, which you said in your case was about the form as well?
Well, that's interesting, because I first wanted, or I prepared a part where I wanted to talk about that Semper stuff, because it's obvious that's an interesting question connected, and I run out of time, and so I left it. But I think one should, the whole thing is, the interesting thing is that it is one whole thing. It's not one before the other. And but on the other hand, of course, one can learn something by Semper easily, and that construction and even stress doesn't produce form at all. Absolutely not. So you have to find, and this is a very simple and very interesting rule out of the 19th century, which somehow got lost. But it's obvious that what the calculation produces, or what the catalog of the construction firm produces, is not form at all. It may be or not. And so we are definitely, and that's one can call manierist. We are working with that knowledge, and so this bridge, as well as all the other buildings we did, are not the result of the calculation of your concept, and he never conceived me like that. So I think this is, but it's also not the contrary. It's not so kind of material. Maybe it's difficult to describe also the process. It's a kind of a research which always moves from, it changed always the direction of looking at the things. There were certain moments where for example, when we had this problem with the shifted walls, where we have been banned by physical problems which have been almost destroying the scheme. So that can happen as well, but it's interesting, this kind of it's also the process which is hybrid somehow. I don't know whether that answers what you mean.